Hi, my name is John Sakizadeh, and today I will be discussing my work on the ligand exchange mediated assembly of a biomineralized nanocomposite photocatalyst. Laboratory synthesis of nanomaterials utilize high temperatures, organic solvents, inert atmospheres, and complex processing, which limit their scalability. In comparison, biological synthesis of nanomaterials occur at low temperatures and in water. Our group has been studying using the process of biomineralization to synthesize metal sulfide nanocrystals in water at room temperature. Recently, we have been interested in using these metal sulfide nanocrystals for photocatalytic hydrogen production. Photocatalysis is the process by which materials absorb light, exciting an electron, which then takes part in a chemical reaction, such as the reduction of water to form hydrogen. Cadmium sulfide supported on reduced graphene oxide photocatalysts have been shown to produce hydrogen at a high rate, but are synthesized using under unfavorable conditions. In this project, we biomineralized cadmium sulfide nanocrystals and reduced graphene oxide and studied the low temperature aqueous attachment of the materials to achieve high performance photocatalytic hydrogen evolution. The biomineralization synthesis of cadmium sulfide and reduced graphene oxide was performed by the single enzyme cystathionine gamma lyase, or CSE. CSE converts the amino acid L-cysteine in solution to form hydrogen sulfide, which reacts with cadmium ions to form cadmium sulfide nanocrystals, or can reduce graphene oxide to form reduced graphene oxide, or RGO, which is an excellent support for photocatalysts, all under physiological conditions. Besides being the sulfur source for the synthesis, L-cysteine also plays the role of a capping ligand, binding to the growing cadmium sulfide surface, suppressing growth, and giving the particles nanocrystalline morphology. The problem in forming a cadmium sulfide reduced graphene oxide photocatalyst is that the biomineralized cadmium sulfide and reduced graphene oxide do not attach as synthesized. This is because cadmium sulfide and reduced graphene oxide both have negative surface charges. The negative surface charge of cadmium sulfide is caused by the negatively charged L-cysteine groups bound to its surface. Therefore, it was expected that by changing the surface charge of cadmium sulfide by exchanging L-cysteine for a positively charged capping ligand would thus make binding possible. Cysteamine, a similar molecule to cysteine minus the carboxyl groups, has been shown to give particles positive surface charges when used as a capping ligand, and was thus expected to give cadmium sulfide a positive surface charge, which would then spontaneously assemble with the negatively charged reduced graphene oxide. To exchange L-cysteine for cysteamine on the cadmium sulfide surface, all that was done was simply adding excess cysteamine to solutions of L-cysteine capped cadmium sulfide. This pushes equilibrium to favor cysteamine on the cadmium sulfide surface. To confirm ligand exchange, we turn to attenuated total reflectance FTIR spectroscopy. FTIR spectra of the cadmium sulfide before and after ligand exchange shows a decrease in the carboxyl signal, while the amine signal remains constant. This suggests that cysteamine had replaced L-cysteine on the cadmium sulfide surface. Attachment of cysteamine capped cadmium sulfide to reduced graphene oxide was performed by simply adding reduced graphene oxide oxide to solutions of cadmium sulfide. UV-Vis spectra showed that by centrifuging out reduced graphene oxide from solution simultaneously decreases the cadmium sulfide UV-Vis signal, while cadmium sulfide signal remains stable when centrifuging without reduced graphene oxide. This indicates attachment of cadmium sulfide and reduced graphene oxide. Furthermore, scanning transmission electron microscopy images confirm attachment of cadmium sulfide and reduced graphene oxide. Photocatalytic hydrogen evolution data shows that by supporting cadmium sulfide and reduced graphene oxide by ligand exchange, significantly increases the hydrogen evolution rate of the material. Furthermore, the mass normalized hydrogen evolution rate of the biomineralized cadmium sulfide reduced graphene oxide photocatalyst was found to be competitive with similar photocatalysts synthesized through high temperature means. This shows that ligand-driven assembly is an effective way to synthesize high-performing catalytic materials. To better understand the interaction between cadmium sulfide and nanocrystals and reduced graphene oxide to lead to the enhancement in the photocatalytic performance, we analyzed the photoluminescence of the samples. Cadmium sulfide nanocrystals photoluminescent light at 530 nanometers. This is shown in the picture on the left. The light is emitted when an excited electron recombines with a hole. When cadmium sulfide is anchored on reduced graphene oxide and an excited electron is transferred to reduced graphene oxide, this transferred electron recombines non-radiatively, and this manifests as a decrease in the photoluminescence lifetime of the sample. Time-resolved photoluminescence, shown in the figure on the right, illustrates how the photoluminescence of cadmium sulfide on reduced graphene oxide diminishes faster than the unsupported photocatalysts, thus confirming electron transfer from cadmium sulfide to reduced graphene oxide. In conclusion, we have shown that through low-temperature aqueous biomineralization and ligand-driven assembly that we can synthesize a cadmium sulfide reduced graphene oxide hydrogen evolution photocatalyst with competitive performance and with similar photocatalysts synthesized through high-temperature means. Future work includes improving the stability of the biomineralized photocatalyst by reducing the corrosion rate of cadmium sulfide by passivating its surface with an insulating shell.